Hello, Maddie.
Hey there, how's it going?
Going well. How are you?
Good. I'm glad your exams went well.
I know I was so stressed
That's-
about it last night. But I'm so glad it's over with right now.
Yeah, I bet. Sounds
Yes.
stressful.
It was so like I was like wasn't sure if I was gonna pass the exams or not, but luckily I did. The scores
Oh,
came.
really? Is it like it's graded then and there?
Yeah, it's graded like right away. Like these classes are graded like so fast.
Oh my gosh, that's
Yeah.
crazy.
I know. So like that's the good part about it. Like the grades come out like at least like at most 1 day or 2 days. So we get to
Right.
get the results ahead of time.
And is it like a pass, no pass type of situation?
It some classes are pass no pass, but most classes are A B C like D the grading scale. But there's
Hmm.
no plus or minus grade. It's just like a solid A, solid B, or solid
Oh
C.
wow. Okay.
Yeah.
Oh my
Mhm.
gosh. Well, major props to you. At least you got through the first part of it, right?
Yeah, first part of it, I do have another midterm tomorrow. So I will be studying for that after this office hours,
Oh my
and
gosh.
a quiz too, and a quiz tomorrow.
Oh gosh. You're packed.
Yes, I am. I am. Uh-huh. But I try to get most of my work done and studying done right after school at the library, and then
Right.
I start driving home around 7:30 p.m. and then do these office hours. But like I eat dinner first, walk my dog, and then like go on these office hours.
Yeah, give yourself some time
Sometimes
to
and breathe,
regroup.
yeah.
Yeah.
Yeah. Hey.
Okay.
Hey, Elysia.
Hi, Bryant.
Let's see. How did the midterm go?
It wasn't bad. I may have messed up on like the NMR
Uh-huh.
spectroscopy, low key. That's why I kind of like I didn't show up these past sessions because like
Uh-huh.
I was just I was trying to catch up on my sleep.
Yeah, your sleep and your other classes too, right? Because like you've been
Yes.
studying for it so much. I know.
Yeah, I was going heavy on the caffeine. Like
Uh-huh.
literally my routine was
Oh
coffee in
my
the
God.
morning, Celsius at night.
Oh my God. That's crazy. That's a
It was
lot.
bad. And like I'm like now I get like the
Mhm.
after effect of like just feeling super sleepy.
Super sleepy, yeah.
Yeah, and I
Uh-huh.
kind of have to catch up on my calc.
Mm-hmm. Yeah, what is your midterm for that?
It's this coming Monday.
Mm-hmm.
I did go back home.
Oh yeah, yeah.
Yeah, I mean
Uh-huh.
like yeah, I kind of just needed to be away. And
Mm-hmm.
so like I
Yeah, yeah, yeah.
and
It takes some
also
time to take a break after the midterm, especially after the midterm.
yeah, I unfortunately I missed a OChem lecture because
Mm-hmm.
my work called me in even though I gave my hours to be only 6 to 8 and they still put me on the schedule.
Oh,
So
they still put AAA, right?
yes, so
Oh
I was kind of
no.
upset about that
Dang.
because like I hate missing lecture. I feel
Mm-hmm.
like even though I'm like, oh yeah, I'll like make it up or whatever.
Or like watch the lecture. Like it's so much harder to pay attention like
That too.
online than in
Yeah, I
person.
mean there's pros and cons.
Yeah, there is. Right. I didn't see like you do any sessions on the Voice app too. I was like, oh my gosh, you're taking a big break. Yeah.
You're seeing how many trees I planted.
Yeah,
Like,
yeah.
and yeah.
Uh-huh. Hey. Uh-huh. So, what we'll do is we'll do 8B stuff today in office hours, and we could alternate between 8B and 118B. Do you
Hmm.
have any topics or questions you want to go over, Madison?
So I've been reviewing, I've been like kind of bopping through, like going down the list of like all the things that
Yeah.
are gonna be on it. I have like two things left to like review, nitration and sulfonation.
Oh, the electrophilic aromatic substitution benzene reactions. Yes, those things.
Are those pretty like easy concepts to grasp? Because I feel like the thing I struggle with the most right now is like
Mm-hmm.
epoxide reactions.
Mm-hmm.
Because like the reactions of ethers is like mainly like the Williamson ether synthesis.
Yeah, Williamson ether synthesis, and the reactions with HX versus H2SO4
HX versus for
with 135 degrees or 180 degrees for ethers,
okay.
right? And that is when we have the ranking list of the R groups. Like tertiary is the highest priority, and then we have primary, and then methyl, and then secondary is the lowest priority. Remember
Mhm.
that list, ranking list, when we have like different R groups, and then we choose the higher R group to be our substrate, making the
Right.
other group the good living group, and then from there we use that chart or table of reactions depending on if we have HX or H2SO4, and it would also matter if we have 125 degrees Celsius or 180 degrees Celsius. But specifically for Leibniz class, if you see this delta symbol or triangle, that means heat. Wait, it's gonna favor both the substitution reactions and elimination reactions. So you have
Right.
to draw both products for Leibniz class specifically. 125 degrees is SN substitution. 180 degrees, the higher temperature one, is gonna favor elimination reactions.
Okay.
Right.
Um, can we go over, do you like briefly sulfonation or like do a problem on that?
Yeah. So before we go over sulfonation, nitration, and all those electrophilic aromatic substitution, I want to go over the general mechanism with you for that. Right.
Okay.
So electrophilic aromatic substitution. You are also going to see that as EAS reaction, right? Where this are the benzene reactions. So let's draw
Mhm.
a benzene out like that. And the benzene in this reaction here is going to be nucleophilic. Right? It's going to be the nucleophile because the atoms in these benzene carbons here are going to have negative charges because there's double bonds all around the ring where we can do resonance by like shifting one of the bonds over to one of the carbons, giving that carbon a pair of electrons like that, and the other carbon that loses the bond a positive charge, right? So just imagine that because this benzene here has a lot of double bonds, it's electron rich. There's a lot of
Mhm.
electrons there, making them nucleophilic. It can attack some sort of electrophile. Right. So let's just bring in some generic electrophile, which is gonna be common for a lot of these reactions that you're learning right now. And let's say that we use this carbon right here that I am starring as the nucleophile. That is going to attack this electrophile right here, and we're going to make a new bond between that carbon and this electrophile right there, right?
Mhm.
This is the starred atom. This is the electrophile. This right here is the new bond between the nucleophile and the electrophile.
Right.
The double bond right there is still there. That's still there. But this double bond right here is no longer there because you could think of it as like shifting over to grab that electrophile right there.
Mhm.
And that's this bond right here. You could highlight it to say that that yellow highlighted bond right there is this yellow highlighted bond right there. And because this carbon here lost a bond, that carbon is now positively charged like that. We know that the benzene is aromatic because it is cyclic, it is fully conjugated, and it is planar,
Mhm.
and it has 3 pairs of electrons doing resonance all around the ring, an odd pair of electrons, which is aromatic. What would you say this molecule is? Would this molecule be aromatic, anti-aromatic, or non-aromatic?
Non-aromatic.
Correct. Non-aromatic, because what condition does it not fulfill?
It's not. It's cyclic.
Mm-hmm.
It's planar,
Mm-hmm.
and then cyclic planar, and then what's the other one?
Fully conjugated
Fully
or
conjugated.
doing resonance all around the ring.
And it's not because of that new bond, right?
Yeah, that's part of the reason, but the more correct reason is because of this sp3 carbon right there. Right, that new bond right there that we created this sp3 carbon, which
Mhm.
is not able to do resonance at all. There's no p orbital there, right? Because of that new bond that was formed right there to that carbon. So we turned a stable molecule into an unstable molecule, right? Now, the last step here is going to be elimination, where we're going to restore the aromaticity. So I'm going to draw out an invisible hydrogen right here because I want to gain our double bond back right there. We're going to do an elimination reaction, E1 type mechanism, right? So some sort of base, let's just say a generic base like that. And these electrophiles and bases are going to be different depending on what reaction you do. There's sulfonation, nitration, halogenation, and Feudo-Caves reactions, right? A base is going to grab that hydrogen, and then the bond between this hydrogen being grabbed and this carbon right here, this bond is going to make that double bond right there, restoring the aromaticity, restoring our benzene ring.
Oh, I see. Okay.
And so our final product here would be this benzene ring that is now happy again because it's aromatic, but now it has a bond to an electrophile like that, right? Because of the first step here. And if this was a mechanism problem, you would have to draw that base out with its proton that it grabbed, with the hydrogen that it grabbed right there.
Okay.
Right. And if this was neutral, then this base would most likely be positively charged. If this base was negatively charged and it grabbed that hydrogen, then it would be neutral. Right. So it depends on what base you use. Right. Because whenever you get protonated, you get +1 charge. Like you always add 1 charge.
Right.
Okay. So that's the basic mechanism of electrophilic aromatic substitution. It's a 2-step mechanism once you have this good leaving group. The first step is addition. The second step is elimination. So this is an addition elimination mechanism.
Elimination. That's the. Is that the okay. This might sound weird. Is that the one where it's like mixed, like it's both what is it, SN1 and looking at my notes. No.
So it's not the one that's mixed because the first reaction is not it's not a substitution mechanism because we're not substituting anything with anything. But the second reaction here is just all elimination, elimination, right? The mix SN1 or E1 is going to be like with an ether, H2SO4, and that heat symbol right here. Like this heat symbol is the mix SN and E elimination reaction.
Okay.
Right. Now, let's go over sulfonation, which is a specific kind of EAS reaction. The general reaction is that when we have a benzene like that, and I give you these reagents, SO3, H2SO4, that's going to add a SO3H group onto the benzene ring, right? You could draw that out in Lewis structure like this. Sulfur, boom, boom, boom. This is the same thing as SO3H because there's 1 sulfur atom and 3 oxygen atoms and a hydrogen like that. Right. Okay, now let's go over the mechanism of how that happened. First, we have to generate our electrophile. Once we have our good electrophile, then we do the 2 steps that we went over. Addition, then elimination. So first step, generate electrophile. I'm going to draw out the SO3 out like this. Oh. Wait, is that the SO3 Lewis structure? Let me see, just in case. SO3 Lewis structure. Yes, it is. Okay, sulfur with 3 double bonds to 3 different oxygens. And we also have H2SO4, which is a strong acid. So the first step here is that one of the oxygens here is going to grab that hydrogen and kick off an HSO4 minus. An acid-base reaction is going to happen, right? Our base here is this oxygen. Our acid here is this H2SO4. So our conjugate acid after that step would be this. where we protonated this oxygen here, which is now positively charged, and we kicked out an HSO4 minus like that, right? Think of this as a good leaving group, right? So I'm just gonna put like an outline around here, so that you think of that as a good leaving group, right? And this sulfur here is now an electrophile, right? That's the electrophile in this reaction right here. So that's the end of the first step. Done. Now we go on to addition. Okay, let's bring in our benzene, and let's bring in our electrophile that we formed. In this case, this is an empty benzene ring, no groups attached to it, no EDG, no EWG, so it doesn't matter which carbon we use as a nucleophile. Right, I'll go over like when it has groups attached to it, but for now, let's start off simple and say like this is an empty, naked benzene ring that has no groups attached to it, no EDG, no EWG. So this carbon here, let's say is the nucleophile, that's going to attack this sulfur and kick off that good leaving group that we said, making this oxygen neutral now, right?
Okay.
So now our intermediate here is going to be this, where this dark carbon here made a new bond to the sulfur, which is this new bond right here. We lost this bond because that bond like grabbed that sulfur, which is now this bond, and this carbon is now positively charged. And now you could go like straight to the next step right away by doing elimination with HSO4 minus, right? But the first time I'm showing you this mechanism, I'm gonna separate them to make it more clear in your head when you think about this mechanism. So you could like make it more sense for you. You know, like you could categorize it. You could break up the mechanism, break down the mechanism. Once we have this non-aromatic ring, then we do elimination to restore the aromaticity. Our base here that we're going to use is the HSO4 minus base that we formed earlier. This HSO4 minus comes from this first step here when we generated the electrophile right there, right? That floats around until the third step of elimination right there. And its job is now to reform the aromaticity like that.
And recreate that double bond.
Correct. Recreate that double bond. As this hydrogen is being grabbed from this HSO4 minus, that bond between the hydrogen being grabbed and carbon breaks and recreates that double bond right there.
Okay.
Which makes it aromatic and stable, right?
Okay.
And I'm going to abbreviate that whole big group as SO3H like that. And if this was mechanism, H2SO4 acid catalyst gets reformed, right? And we sulfonated our benzene ring here. We added a sulfonate group to the benzene. That's that new group right there.
Okay.
Right. Okay. So if this is a mechanism problem, you did not have to like separate the addition and elimination step, because straight after you got the product from the addition, you could go straight to the elimination step right away with HSO4 minus, grab that hydrogen, recreate that double bond, and then go straight to the product right away, just like that.
Okay.
But that's how you could think about the mechanism. So it makes more sense, and you could recall it when you take the exam or practice with this mechanism.
Okay. I had a question in my mind. And what type of reaction would you call this?
This reaction here is, well, the mechanism is, well, okay, reaction is sulfonation specifically, but the mechanism is electrophilic aromatic substitution. That's the mechanism. Yeah, because I know Levens is like a big, she makes it a big deal about what's the mechanism name, what's the reaction name.
Right.
So the reaction name, sulfonation, mechanism, electrophilic aromatic substitution. But a lot of reactions can do this, electrophilic aromatic substitution, nitration. Well, that's five, right?
Okay.
Yeah.
I have a question.
Yes.
Wait, can you hear me? I don't know if it's going through.
Yeah, I can hear you.
Okay. So we just did sulfonation. Is halogenation and nitration basically the same process? Because those are also going to be on the quiz.
Yeah, halogenation, nitration. Did you learn about Friedel-Crafts alkylation, Friedel-Crafts acylation yet, or not yet? Or is that not on the quiz?
We did, but yeah, it's not on the quiz yet.
Wait, is this tomorrow's quiz?
Yeah.
Oh shoot.
Yeah.
Oh my gosh, with EDG and EWG as well?
No, we didn't learn that yet.
Oh, so it's just an empty naked benzene ring reacting with
Yeah.
okay, that's good. Because if
Yeah.
there's wait, I'm abbreviating it. What about electron donating group, electron withdrawing group? That's the full name. Electron
Yeah.
donating group. You learned about that? Is that on the quiz?
No, it's not on it yet.
Okay,
I was
okay.
doing some of the
Uh-huh.
ATC practice, and I realized that like I was trying to figure things out that we didn't learn yet.
Mm-hmm.
So
Yeah.
yeah, that's not on it.
Oh, okay, that's good. So Elysia, do you have any 118B questions you want us to go over today? Because 8B has their quiz tomorrow, and this is a pretty big topic. EAS reaction mechanism. Or did you have any topics you want us to go over, Elysia? Uh-huh. Wait, that's weird though, because the practice quiz that she posted right here, there's no EAS reaction in this practice test. It's ether,
Yeah.
epoxide, vocab. There are aromatics, anti-aromatics, and non-aromatics too with nomenclature.
I think
Identification. Yeah.
I think there's some on there that there's a couple questions that are on the practice quiz 3 too. She said like questions like
Oh, really?
I don't know. I haven't looked at that yet.
Okay. What we'll do is we'll go over all those reactions, halogenation, nitration, with the mechanism, and then after that we'll do those practice quiz problems that Maddie just mentioned. Okay. So let's do halogenation, which is going to either be mostly bromination or chlorination. I don't really see iodination. I never heard of that too before. Or fluorination. I only see bromination or chlorination of a benzene ring.
Yeah,
Right,
that's
most
what we
likely.
learned.
Right. So the general reaction of this is that we're gonna have a benzene like that, and the reagents are, let's do bromination. Right. X2. Wait, let's make it generic actually. X2, where X can be bromine or chlorine, and you would need a metal catalyst for this reaction. You need AlX3 or FeX3. Right. Is it X3 or X2 for Fe? FeBr3. Yeah. FeX3, where X can be bromine or chlorine. And these are called metal catalysts. You could also see this as Lewis acids, yeah, aka Lewis acids. Do you guys remember the definition of Lewis acid back in 8A?
No.
No? Okay. That's okay. So a Lewis acid is going to be a molecule that can accept electrons. Right. And the reason why these are Lewis acids are because if I draw out the Lewis structure of AlX3 and FeX3, we see that aluminum and iron have 6 electrons only. They don't fulfill the octet rule. That means that they are missing 2 electrons and they have an empty p orbital. And because they have the empty p orbital here, they can accept electrons. They want to accept electrons. They want to be attacked by some nucleophile. Right? Okay, so that's the metal catalyst. Let's now go. Wait, let me finish up this reaction. This reaction here just adds a halogen to the benzene like that, whatever the X is, bromine or chlorine. Okay, the first step, generate the electrophile. Okay. The first step here for these EAS reactions are going to be the hardest one probably, right? Because it's gonna be different for all different reactions. But once you get the good electrophile, it's easy from there, right? Because it's just the addition and the elimination step. For halogenation, our generating electrophile would be something like this. Let's say we have Br2. I'm gonna draw out Br2 like that using FeBr3. FeBr3. I'm gonna draw out all of these bromines, pairs of electrons like that, where we said earlier that this iron has an empty p orbital, right? It wants to be attacked. It's our electrophile here. So one of the bromines here is going to attack that electrophile, and that's it, right? That's the first step. And let me show you what the electrophile is right here, actually. But when that happens, what charge would this bromine have now after this step?
Would it be a negative charge?
So to calculate formal charge, we look at how many...
formal charge.
Formal charge, yes. It wants 7 electrons because it's on the 7th column, 7th group, and then we calculate how many electrons it has to itself, right? A bond counts as 1 electron it has to itself, and then a lone electron counts as an electron to itself. So it has 1, 2, 3, 4, 5, 6 electrons to itself right now, right? So 7 minus 6 would be positive 1. So this bromine here with 2 bonds and 2 pairs of electrons would have a positive charge like that, right? And iron right here, because it's one of those weird atoms like boron, aluminum, iron right here, when it has 4 bonds, it's going to be negatively charged. And I'm going to circle my good leaving group right here. This right here is my good leaving group, because when it leaves, it could leave with a stable like pair of electrons, right? This bromine right here on the other side is going to be my electrophile, my substrate. Leavens calls that substrate sometimes. Substrate. Okay, that's the end of the first step. Now the second step, addition. Let's bring in our benzene like that, and let's draw out the electrophile we just generated in the first step. Oh shoot. Br3, negative charge, positive charge, negative charge. Okay. So let's just do this. Attack, kick out the leaving group, break the aromaticity, unhappy, sad, benzene ring, unstable benzene ring. Oh, not benzene anymore. Right. Bromine. And I'm gonna say this is FeBr4 minus charge, like that. Right. That's the end of the first step, addition step, where this carbon here is the nucleophile that attacks this electrophile and it kicks off this whole leaving group right there. Right. This bromine right here is now going to be neutral because it gains a pair of electrons, but the iron here stays negatively charged because the iron there still has 4 bonds to bromine like that. Now our elimination step is to restore the aromaticity of the benzene ring. And our base here to do that for this specific reaction is going to be the FeBr4 right there. So I'm going to draw it out in its Lewis structure, because this is the weird part. Like the iron molecule is the weird part here. This iron with 4 bonds, 1, 2, 3, 4, has a negative charge, right? So that means that one of these bromines here are going to be our nucleophiles. Doesn't matter which bromine you choose. It could be this one, this one, or this one, or this one right there. I'm going to choose the closer one because it is easier to grab this hydrogen right here and generate a double bond right there, which restores our aromaticity like this, right? And we also reformed our acid catalyst, right? Our metal catalyst. We reformed our FeBr3 like that, right? Because this iron here has 3 bonds to bromine. It's neutral because it's one of those weird atoms like boron or aluminum, but This is what we started with, the FeBr3, our metal catalyst, gets reformed right there. And we get our final major product, that brominated or halogenated benzene ring. Like that. The weirdest part of the mechanism here, or reaction I would say, is generating the electrophile and determining what's the good leaving group and what's the substrate once we do that, right? This molecule here looks very weird the first time you look at it, right? But when you have something like this, one of the bromines is going to be the electrophile, the neutral bromine in particular, whereas the positive charge bromine with the metal catalyst is the good leaving group right there, right? Because the good leaving group will leave with this bond right here when it breaks off and goes to that bromine when something attacks it, right? Just like in this addition step here. When this carbon here attacks that bromine and we kick off that leaving group, we get this like set of intermediates in the mechanism, you could say. Yeah.
So is the bromine that doesn't have a charge, that's neutral, right?
Correct.
Once
This bromine here
leaves?
is neutral, and this bromine here with the positive charge will become neutral, right? As it leaves. Like this bromine here with the positive charge will become neutral. Because if I draw you out the FeBr4, that's going to look like this. This is the iron attached to 4 bromines. 1, 2, 3, 4. And iron is one of those weird atoms that has a negative charge when it has 4 bonds, right? This bromine here that was positively charged, let's highlight that in pink. Is going to be, let's say, that bromine right there. It became neutral because it gained a pair of electrons from that bond right there, right? Before, it had 2 pairs of electrons, 1, 2. But when it leaves, right, this whole leaving group leaves, it gains a pair of electrons from that bond right there being broken, right? That bond between the bromine being grabbed from this nucleophile and bromine right there, those 2 electrons kick off onto that bromine, giving that bromine an extra pair of electrons. So it would now have 1, 2, 3 pairs of electrons, 1 single bond, neutral, if you calculate the formal charge, right? Because it has 7 minus 1, 2, 3, 4, 5, 6, 7 electrons. 7 minus 7, 0. Net charge of 0.
Okay.
And if I highlight the bromine being attacked here in blue, that's this blue bromine right there, which is attached to this carbon now. That's red starred carbon that I starred right there, like that. Right.
Oh, okay.
Let's highlight the bond here that is lost in red. That's the bond that is grabbing that bromine right there, that electrophile right there, which is this red bond right there. Right? Because that's why we don't see that red bond anymore in the benzene, because it went and grabbed that bromine, which is this red bond right there.
Oh, okay.
Yeah, it's a lot of, you know how it's like so many minor specific details of where the atoms are located, where they came from, where the bonds came from, where the charges came from. It's a lot of keeping track of where did that come from, where did that come from, like how'd that guy get there?
Yeah.
Right. And
But I feel like
mhm.
I feel like if she were to ask just like what the final product is, wouldn't it just be easy to just like copy the benzene and add the bromine?
Yeah. Right.
Okay.
It's easy.
That's pretty much like, I think what most of it it's like is, right? Is like just predict the final product.
Yes.
Yeah.
If you just have an empty benzene like that with no groups attached to it, then that's very easy.
Right.
But if you do have groups, those groups could be different. They could be considered an EDG or an EWG, and those groups will direct where the electrophile will go. Will direct where the halogen here in this case will go. It doesn't matter where you attach it to the benzene ring.
Okay.
But I want to look at your quiz and see like what she told you to practice on to see if that has those groups. So let's look at that now.
I just looked at the third quiz, and the problems that she said to go over on the third quiz are just like the word problems. It's there's no reaction problems that she like referenced, but I'll drop it in the chat.
Yeah. Yes. Yeah, you can drop it in the Zoom
Okay.
chat.
I think this is the one with the key.
Yeah. Thank you. Is ortho meta para included in the quiz? Those vocab terms, ortho meta para?
Yes.
Oh, it is. Okay, let's go over that too.
Yeah, that would be great.
Wait, are they gonna be on tomorrow's quiz though? She
I
didn't
believe
talk about them.
they're on the
Really?
practice quiz too, like in the vocab
Oh
section.
wait. Oh, just for nomenclature though, right? Not to know how to do reactions.
No, not like reactions, just being able to identify like what like
Ortho meta
structures
para
are
is.
ortho, meta, and para. Yeah.
Yeah. Okay.
Yeah, I can't do the react.
Yeah.
Not yet.
Oh no. Oh shoot, yeah, the mechanism for this quiz that you just sent me is nitration.
Oh
Nitration. Is that included? I know she like it's an announcement of like different parts to focus on the quiz.
Yeah.
What parts are focusing on?
So in this, I can send you the screenshot too. It says practice quiz 1, all the problem, or 1 BD AC 4, practice quiz 2, which was the one earlier from yesterday, which was all of them, and then practice quiz 3, 4, problem 4, E and F.
Oh, so the vocab questions, no nomenclature, no reactions. Okay. 4F. Aromatic molecules typically do or do not react under the same conditions as alkenes. Okay, 4F. Is there anything else like this quiz 3?
Unless she like missed putting on question 3 on there, like she mistyped it.
Like the mechanism problem for this?
Yeah.
Okay. Yeah. But I can explain that concept if you guys don't understand it. Like, do you guys know why aromatic molecules typically do not react under the same conditions as alkenes? Right.
I feel like
of their
Go ahead.
I don't know.
It's okay. Give it a guess.
Don't they have like ring strain, like their SP, like the way they're oh gosh, structured?
So ring strain, right? That's going to be unstable rings, and you're gonna see that with 3 and 4 membered rings. So the rings that have ring strain is cyclopropane and cyclobutane, like that. These are the molecules that have ring strain, right? That's because like we were taking the hybridization of these carbons here are sp3 carbons. All of these carbons in green are sp3 carbons. And what's the preferred bond angle for sp3 carbons?
It is it 109?
109.5
or 5
degree bond angle, right? But what is the bond angle that this bond is forced to be in this equilateral triangle? Let's do math here. We're gonna do some math in here.
Isn't that 60?
Yeah, 60 degrees. That's so unstable, so unhappy, because there's a big difference between 60 and 109.5. That's not good. We don't want that. That's ring strain. That's what we call ring strain. What about this square or cyclobutane? Just draw the angle out like
Those
that.
are 90?
90 degree. Right? That's also a lot of ring strain because there's a big difference between 90 and 109.5 as well.
Right.
And that difference is what we call ring strain.
Okay.
But once you get to like 5 and 6 membered rings, they start to get closer to 109.5. Like the bond angles between these bonds here are gonna get closer to 109.5. No ring strain there. Right? Okay. But for aromatic compounds, right? Let me finish this off. Aromatic compounds typically do not react under the same conditions as alkenes. Because let me draw you a basic aromatic compound, benzene, and a simple alkene. Which one would you guys say is more stable?
Oh,
The
no.
benzene.
Yep, more stable, less stable. So if that's the case, which one has more energy?
More energy.
On the
Mhm,
right.
more energy. The one on the right, right? Because energy and stability are inversely proportional, inversely related, right? The more stable molecule, the more happy molecule is less angry, less energy. The unhappy molecule, the angry molecule will have more energy, right? And because that's more energy, it's going to be more reactive. The benzene that is more stable, more happy with less energy is inert. It's going to be less reactive, unreactive, right? So that's why aromatic compounds are typically do not react under the same conditions as alkenes, right? Because if I put HBr in this alkene, what would be the major products here?
Good boy.
Was this quiz 1 or AA? I forgot. for alkene reactions.
I think this was quiz 1.
Quiz
right?
1, alkene reactions? Markovnikov, anti-Markovnikov.
Oh, did we learn? I don't think we learned.
Oh, I think
No,
this was
that was
AA. This is the
A.
end of end of AA for you guys. Yes. This is the beginning of 118B. Beginning of 118B.
Wouldn't this be, I might be totally wrong, but elimination reaction?
So it won't be elimination reaction because elimination reactions creates double bonds.
Oh, right.
But this right here will add bromine to the more subside, right? That's how you would predict the product. It's not always the case because you have to look out for hydride shift or methyl shift and see like if you can do carbon cation rearrangement. In this case, there's no shift. So I don't think this mechanism is gonna be tested, so let's not worry about that. But if we try to do the same conditions with this benzene here with HBr, right? We do have 3 alkenes in here, 1, 2, 3, but those alkenes are doing resonance with each other. They're fully conjugated, right? And we don't want to break that conjugation. We don't want to break that resonance that's going on between them, because that would break the stability. That would make it more angry, less happy, right? So there's no reaction here because of the resonance going on here, the aromaticity going around right here, right? This alkene right here, on the other hand, is not aromatic. It's not cyclic. It's not planar, and it is not fully conjugated. So because of that, it's not aromatic, less stable, more energy, more reactive. It will react, right? Whereas the benzene here, because it's stable with aromaticity, it is less reactive. So that's why it would not react with the same conditions, HBr, for example. Right. That's why when we do electrophilic aromatic substitution reactions, benzenes can do the reaction because we're adding some sort of catalyst in the reaction. And back in Gen Chem, catalysts speed up the reaction, right? By lowering the activation energy. This right here is a metal catalyst. In sulfonation, we had an acid catalyst. This H2SO4 here is an acid catalyst, which speeds up the reaction and makes the reaction able to go through. Right? Like that. Yeah. Okay.
I had another question about stability of rings. So she had a participation quiz, and one of the questions was saying aromatic molecules are either more stable or less stable than non-conjugated alkenes. Aromatic molecules are more or less stable than conjugated alkenes, and then anti-aromatic molecules are more or less stable than non-aromatic molecules.
Mm-hmm. Yeah, and
So
those
I
are all
didn't know
true
which one.
statements, or did she tell you to like say which statement is true or false? Like, was that the question? Like, which statement is true, which statement is false?
Um, no, it was like we had to choose if it was more or less stable than the other. So the first one was between aromatic molecules and non-conjugated alkenes.
Mm-hmm.
So if aromatic molecules are more, less, or equal in
Mm-hmm.
stability.
Mm-hmm. Yes. So let's take a look at that. Let's bring in that aromatic molecule, and let's bring in this non-conjugated alkene. That was the example that we just did right here. Where
Oh,
is it? Oh, where is it? Right here, right here. So this is our aromatic molecule, and this is our non-conjugated alkene. This is a non-conjugated alkene because it cannot do resonance. Whenever you see conjugation or any conjugated term, associate that with resonance, right? Conjugation
okay.
is going to be interchangeable with resonance. This alkene cannot do resonance, right? So the aromatic molecule would be more stable, right?
Okay.
Mm-hmm.
And then aromatic molecules versus conjugated alkenes.
Mm-hmm. Aromatic and conjugated alkenes that are not aromatic, and that would be something like this, right? So this alkene here is conjugated because it could do resonance with the molecule, but it's not aromatic because it does not fulfill the cyclic rule and the planar rule. Actually, all atoms here are sp2, 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 sp2. So it could be planar because all atoms here are sp2, but it does not fulfill the cyclic rule, so it's not aromatic. Aromatic would be more stable still. Well, this is kind of a gray area because it depends on how big the conjugated system is. Like if it could do a lot of resonance, like a lot more than aromaticity, that this can start to become more stable. But I would say for the quiz, I would try that. Try aromatic first.
Wait, I don't get the difference between that and the non-conjugated alkene. Like they're both the same, just a longer chain.
Mm-hmm. Yeah, so I could also do like this as well, right? Where this non-conjugated alkene right here is that saying that this alkene here cannot do resonance with anyone, anything. It cannot move here because that's sp3 roadblock. It cannot move here because that's an sp3 roadblock, right? But if we focus on this alkene right here, it could do resonance here. It could do resonance here because there are p orbitals adjacent to each other that are able to do resonance conjugation. They're able to flow around, right? Conjugated. This alkene here is conjugated. Right. It could do resonance
because there's p orbitals all around, but non-conjugated would mean that we only have one p orbital, but like different hybridizations around it that would stop it from doing resonance.
Yes, the sp3 roadblocks, because when you see one double bond, it's not always conjugated. I mean, when you see multiple double bonds like this, it's not always conjugated because you can have a molecule that's like this, where there's two alkenes, right? But these two alkenes here are not able to flow with each other, are not able to do resonance with each other, right?
Okay.
And that's because of this sp3 roadblock that's blocking the resonance right there.
Yeah.
Right. That's not making this able to go do resonance like that. So this is non-conjugated, no resonance.
Just to clarify, the bottom one would be conjugated?
Yes, the bottom one here would be conjugated because all of these alkenes here can communicate with each other, can do resonance with each other, and flow with each other. Yeah.
Okay. And then the last one was anti-aromatic versus non-aromatic.
So this one here, I'm gonna tell you the answer. It's non-aromatic because of something about the, what was it? Orbitals, right? Molecular orbital theory. Some anti-orbital going on here. Some anti-orbital stuff that is not good. I have to like read more into that. That's gonna get more into physical chemistry, like P-chem.
Oh.
Right.
Okay.
That's P-chem. Yeah. But just know that aromatic is the most stable, then non-aromatic is the second most stable, and then anti-aromatic, think of that as the least stable. When you see anti, think of that as like the least stable one. Right.
Okay.
Yeah.
Okay. Okay.
Mm-hmm.
Got it.
Oh, you guys have to take PChem for your major at UC Davis, or no? You guys don't have
No.
to. Okay, that's good.
No.
That's
Thank
good.
God.
Did you
Yeah,
take BChem?
I did.
Oh no.
You. Oh my God.
It was 2 quarters though. It wasn't like 3 quarters, like 118.
Mm.
But mm, it was like physics, OChem, and calculus all combined in one
Ooh,
class.
Wow.
I know.
that's insane.
Yeah.
Yeah.
Uh-huh.
Would you be able to throw a couple
Uh-huh.
examples or like problems for the
Ortho
aromatics
meta para.
on there? Or that too, actually.
Yeah.
Review.
Mm-hmm. So ortho meta para for nomenclature are position terms, right? Position terms between two
Right.
groups, or relationship terms. If I have a di-substituted benzene ring, meaning that there's two substituents, substituted, so many T's and I's, right? Substituted benzene rings. We have 3 ways that those two substituents can be attached to the benzene ring, right? And I'm going to draw those 3 ways out right now, right? So let me draw the template. 1, 2, 3. One way could be that these two substituents are right next to each other, adjacent to each other. Another way is that the two substituents can be separated by 1 carbon. Another way is that the two substituents can be separated by 2 carbons, right? And there's a specific name for the relationship between these two substituents. If they are right next to each other, adjacent to each other, that's what we call ortho relationship. They are ortho to each other. If they're separated by 1 carbon, that's what we call meta to each other. And you could think of it like kind of like an M. They make an M, they trace an M for meta. If they are 2 carbons away or parallel to each other, they are para to each other. Right. Yes, for nomenclature, that's what you need to know about them. And these right here would be important to know when you learn more about the reactions and where the groups direct the electrophiles to go, right?
Okay.
Okay.
And that's just for benzenes, correct?
Yeah, for
Okay.
di-substituted benzenes, or yeah, you can only use ortho, meta, or para in the nomenclature if the benzene only has exactly 2 substituents.
Okay.
Right. If the benzene has more than 2, then you can't use that.
Okay.
Yeah.
Got it.
Yeah.
Okay. I think that's it on my end.
Mm-hmm.
Will these notes be posted today?
Yes, they will. It's gonna be on the school website,
Okay.
like on the classroom and under this today's office hours.
Okay, perfect.
Yeah. Let me give you guys practice problems to end up with for the quiz. Or do you guys want to practice nomenclature, reactions, conceptual questions, vocab? I hate it.
Predict the products? I don't know.
Predict. Oh yeah, predict the product.
Yeah.
That one too.
Yeah.
Mechanism. I
That's
forgot about
reasonable.
that. Okay. Let's do that.
I also have a quick question about ethers after you do these problems.
Mm-hmm. Leavens doesn't really do acid workup for this one, so let's not do that. Ethers, HX, H2SO4, epoxide ring opening. Oh, okay. Yes. So just for extra practice, right? Think of this as a reactions and mechanism problem. When you predict the products for these, draw out the mechanisms for all of these as well, just to practice the mechanism part of this quiz.
Okay.
Thank you.
Yeah,
Thank you
of
so
course.
much.
And what was the question you had, Jenna?
So this is another quiz question. It's asking if primary ethers break faster or slower than secondary ethers, and what kind of mechanism it does in the presence of a HX.
Oh, I forgot to also say, whenever you see these HX reactions with the ethers, think of one equivalent of HX, one equivalent. Right.
Okay.
So one equivalent HBr, anything else? Yeah, okay, so it's that. So the question was asking why primary ethers are faster than secondary ethers in the presence of HX.
No, like it's faster or slower.
Is it faster or slower? Okay, okay.
Yeah.
So that's gonna talk about this ranking list where tertiary is the fastest, and then primary, and then methyl, and then secondary is the slowest, the least priority. When you have a tertiary ether, that's gonna favor SN1. Primary is SN2. Methyl is SN2. And then secondary is a weird mix, right? It's a weird mix, but it's gonna do SN1. But based on experiment lab data, this is the ranking list that the scientists found, where primary would be faster than secondary because primary would do SN2 reaction, would do an SN2 reaction, right?
Okay. What was the primary greater than secondary that you wrote at the top?
Oh, that's what talk about the speed, like primary faster.
Primary is faster than secondary, and then tertiary is the fastest.
Yes,
faster
the
than
fastest.
Primary.
Right.
Okay.
Takes the priority.
And then tertiary. Okay. Okay, yeah, that was it.
Yep. Let me give you guys the key for this for you guys as well, so you guys can check your answers afterwards. After you guys try it. Don't look at this now. Just let's see here. Let me just try the key. Okay. But I won't do the mechanism. That's you guys will look at the note card for that in the notes. I'll just give out the products here.
Okay.
Thank you.
Okay, number 3 is gonna change because I just realized something. Okay, good thing I'm going over the key right now because I just saw a typo for number 3. Ether, alcohol. Let's do this one. That. And that. And this. Let's change number 3. Okay, much better, much better. Okay. Ooh, okay, I'm just realizing that there are some changes that I'm gonna show you guys to the problem.
Okay.
1, 2, 3. Okay. Okay, and then the last one, just fast. Oh, which one? Oh no, this is another one. S. H. Okay. I changed up number 3, the reactant molecule, and I changed number 4's reactant molecule as well.
Okay.
Everything else stayed the same. Yeah. Okay. Yeah. Okay, good luck with your quiz tomorrow, guys.
Thank you so
Thank you so
much.
much. Good luck on your
Appreciate it.
Oh
exam.
yeah, another visit. Yeah, I know. Thank you.
You have
goes
another
well.
exam?
Tomorrow, yes, I do.
Oh my god. How
It's
were
okay.
the
It's okay.
2 that
We're
you did
gonna be studying
today?
together tonight.
Yeah.
Yeah. Uh-huh.
Well, good luck.
Yeah.
Yeah,
Thank
good
you.
luck.
Bye. Good night, guys. Oh yeah,
I
Jetta.
actually,
Uh-huh.
hey, yeah, I wanted to talk to you about the tutoring.
Uh-huh.
So, yeah, I confirmed with my mom and she said that she'd be willing to do it. So what's
Uh-huh.
like the best payment plan, or like how should I send you the money? How should we do it?
Yeah, so I could give you my number in the chat, and then you could either Zelle me or Venmo me. Which one would work for you, Zelle or Venmo?
I think Zoe would be better for me.
Okay, yeah, and then we could like communicate through there as well. And when you have
Okay.
like any questions, text me because that's part of the bonus of the package. Like you could text me, and then as long as it's quick, I can like answer you quickly. But if it takes a while for me to explain like the mechanism or synthesis type problem or NMR, I could go over that during office hours. But if it's like pretty quick to text you like the answer back, then I'll text you back. But if it's long, I'll let you know. I'll go over that in office hours.
Okay, sounds good.
Right.
And then I'll just yeah, will you send me like the details for the payment and stuff?
Yes, I'll send you the details there. Just send me a text and then I'll send you more details, Jenna.
Sounds good. Thank you so much.
Yes, of course, Jenna.
Appreciate it. Good
Oh yeah,
luck.
I forgot to ask. How did your midterm go today? Because I know you said you had midterm today on Thursday.
Yeah, it was Biz 101, my genetics
Oh, your
class.
genetics one? Oh my gosh.
Yeah.
How'd that go for
It
how'd that
was
go?
I don't know. Like I was feeling okay before, and then I started doing more practice, and I realized I was getting them wrong.
Oh
And
no.
then on the exam, it was just so intense, like 2 hours straight of just Punnett squares, and
Oh my God. And
it
you have
was
those
too
like
much.
4x4 ones or 8x8 ones, those big ones too to
Yes, the
work on?
big ones.
Oh
Yeah, and
no.
then like, ugh, no, it was just too much. My head was hurting after. But yeah, I hope.
Uh-huh.
I have no idea how I did, honestly. I'm just
Who's your
hoping I
professor?
passed it.
Yeah.
Ellison, she's really
Oh,
good.
uh-huh. Right. The
Yeah,
material's like really hard though. Like I remember
it
taking that
is.
class. Mhm.
Yeah, no, I was not enjoying that.
Yeah, I see, I see. That's good. But now you got the OCAM quiz to work on and study for tomorrow.
Yeah, yeah,
hmm
I literally did not get a break.
Oh. It's okay. You got anything next week? Like, is it chill week for you next week? Or you got
Yeah,
exams
pretty chill
coming
next
up?
week.
Okay, that's good. So you get
No,
to,
nothing
yes.
next week, so that's good.
Mm-hmm.
I'm gonna try to focus on OChem this weekend.
Mm-hmm. Yeah, that's good. That's good. Yeah.
Um,
Uh-huh.
yeah, well, good luck
Yeah.
on your what exam?
It's eyes, ears, and nose, like all the pathologies, and the different
Whoa.
like things that goes behind that. So it's gonna be a lot of conceptual stuff, memorization is for sure, but the names of like the pathology, the disease, what they
Yeah.
look like, what they present with, the symptoms. So I'm gonna have to Quizlet it out, flashcard it out. It's more of a
Oh yeah, no,
memorization.
that's the best way.
So
Yeah.
yeah.
Good
But
luck with that.
I got it. I got it. Thank you, Jenna. I
I
need
believe in
it.
you.
Thank you. Okay, well, good night, Jenna. Good luck with your quiz tomorrow.
You too. Good luck with your midterm.
Yeah, thank you.
Bye.
Bye.